system. On the one hand, you're looking for a point of intersection, right? You want to see where those two graphs are intersecting. But on the other hand, you're looking for a coordinate that works in both equations, makes both equations true. So that's what we're looking for. We're looking at multiple graphs on the graph at the same time. We're looking for the points of intersection, which means those coordinates should make both equations true. And then, all right, what is the formula for the inverse method? So at the end of the last class, we saw that you can effectively not ever solve systems of equations ever again for the rest of your life. You don't have to do substitution or elimination. You can just use the inverse method on your calculator. So given any system of equations like 3x minus 2y equals -9, and then 4x plus 8y equals 2, you can take this and turn that into one matrix. So A is equal to 3, -2, 4, 8. You type that into your calculator. You take this part and turn that into another matrix, B equals -9, 2. And then you just type that into your calculator, and the answer is going to be x equals A inverse B. Whatever answer you get out of that, like let's say the answer is 3, 9. Then what does the 3 represent? What does the 9 represent? Yeah, exactly. It represents the order of the variables in your original. So in the original, my variables went in the order x, y. So down here now, the 3 is what x equals, and the y is what 9 equals. So you're probably looking at the inverse method thinking, why on earth would I ever solve a system any other way besides just plugging it in my calculator? That's a really good point. This is the most convenient and fastest way to do it. But on the other hand, A inverse isn't always defined. So for any given matrix that you write down, A inverse might not be calculable. Either your calculator could say error, undefined. And what does that mean? If the inverse matrix is not well defined, that means you can't calculate a coordinate of intersection, which tells you what about the original system? Parallel. Yeah, they're either parallel or overlapping. So unless, the system is parallel or overlapping. So you can only actually use this inverse method if the lines are actually intersecting in a normal kind of way. Not if they're parallel, not if they're overlapping. So if you did get an error message saying error non-singular, the matrix does not have an inverse, it still tells you something. It tells you that the matrix, it tells you that the system is parallel or overlapping. And then you just go and investigate it in some other way to verify that. Okay, and then finally, at the end of last class, we talked about how to solve a nonlinear system. So let me just ask you, did we finish all of the nonlinear systems? Wait. There we go. Did we do all 4 of them?
We stopped after we finished 4.
Okay, so we still need to do number 5 then, right? So we'll go ahead and do 5 as an example of a nonlinear system, and then we'll proceed with class. So let me see here. How do you solve a nonlinear system? The answer is either substitution or elimination, because you actually can't use the inverse method always if it's a nonlinear system. In fact, you can't. You can't use the inverse method if it's a nonlinear system. Okay, so we'll start there. What else do we want to say? This is our calendar. There we go. So today is April 22nd, right? Is it right? Of course it doesn't say. Yes, it is. April 22nd. So this week we get to look at chapter 9. And then next week on the first day you have a test. On the second day we get to review for the final exam. And I will give you a practice final. In fact, did I already post the practice final online? I feel like I did. Well, I have a practice final for you, and I'll print out a practice final for you and give it to you this week. And then at the beginning of the next week, you get to take your final exam. So that's where we are. I don't think I told you the NASA joke, did I? I don't think I did. How does NASA organize a party? They plan it. They plan it? Plan it? Okay. Let's see here. So we are, well, I did set up 2 jokes for this week. What does a dog do that a human steps into? This is a good joke. What does a dog do that a human steps into? Pants. What does a dog do? He pants, and the humans step into pants. And you were all thinking something else, weren't you? All right. So let's see here then. The last system question. Okay, so number 5. Let's look at number 5. It's a nonlinear system. What are those two shapes? Does anyone know off the top of their head? Yeah, it is a parabola and a circle. So if you take a look at number 5, the first equation, x plus 2y squared equals 2. Now, normally a parabola is x squared, y and x squared. This is x and y squared, so the parabola is not up and down, the parabola is sideways. So what we have here is a sideways facing parabola. And then the second one, x squared plus 4y squared equals 4. Normally, x squared plus y squared would be a circle, but this one has a coefficient on it, so it's a squashed circle. And so I believe this is an ellipse lengthened in the x direction. So what we have is a ellipse, this longwise, horizontally, and then a sideways facing parabola. So how many times can these two things interact? Well, it could be none, it could be 1, it could be 2. Anything more than 2? Yeah, we could do 3, right? Like if it was like that. And in fact, couldn't we do 4? There. So yeah, there's a variety of different ways the system could look. We have no idea what the system looks like until you graph it. So let's take a look. This is x plus 2y squared equals 2. Oh, they're facing that way. And then x squared plus 4y squared is 4. All right, and so what case is it? How many points of intersection? It's just 3. Okay, so we have 3 points of intersection. The solutions are pretty simple. Go ahead and draw a graph. The points of intersection are at 2, and then up 1, down 1. So let's draw a picture of that. And then when we finish our solution, we should be able to verify that. So the actual, the actual system looks like this. Go. And that was at 2, that was at 1, and that was at -1. There we go. So that's what we're expecting. So what should we do with the system then? We can either do substitution or elimination. What we can't do is plug it into a calculator because we don't have the same variable types, and furthermore, you can only use a calculator for linear terms. So you can only use this calculator trick if the variables are just x, y, z, w. It can't be x squared or y squared. So what would you all like to do? We could do substitution for which variable? We could do substitution for x. Now you can, if you really wanted equals 2, and turn that into x equals 2 minus 2y squared, and then take that and plug it into the other equation's x. But I think pretty quickly here I'm going to say no, I don't want to do that, because I have to FOIL a y squared term, which would give me 4 minus 4y squared plus 4y to the 4th plus 4y squared, and I don't want to solve something that's y to the 4th. It's needlessly complicated. So we just turn around and say, okay, well, forget that approach, let's try the other approach. Because that one looks like it can be tricky. So instead, what can we do? Instead of substitution, can we eliminate x and x squared? No, because they're different variables. That's an x squared. But we can eliminate y squared. So here we have positive 4y squared. We want a negative 4y squared. So we'll go ahead and multiply that top equation by -2. That gives us -2x minus 4y squared equals -4. Ooh, this is very exciting because not only do the y squareds cancel out, but the 4 and the -4 cancel out as well. So we have x squared minus 2x equals 0. Now, just like trying substitution would have been needlessly complicated with that y to the 4th term, look how simple this one turned out. By doing elimination, we got down to x squared minus 2x equals 0. What do we do here? You just take out an x. You could think about doing the quadratic formula where a is 1, b is -2, and c is 0. But I think it'd be much faster just to factor out an x. You have x times x minus 2. And then you have the zero product rule. And you say either x is 0 or x is 2. And that bears out on the graph. Either x is 0 or x is 2. So recall, when you're doing a nonlinear system, each of these are separate alternate realities. Right? You're saying, okay, on the one hand, x could be 0. On the other hand, x could be 2. So on the one hand, we say, let's say x is 0. What comes from that? If we say that x is 0, we have to go back into one of those other two equations. Which one would you all rather plug it into? The first one or the second one? Probably the first one, because it's just x. Less computations be there. So I'm going to take my x plus 2y squared equals 2 equation. Plug in 0 for x, which is nice and convenient. And so I'll just solve for y now. Y is being squared multiplied by 2, so I divide both sides by 2. And I get y squared equals 1. And so square rooting, I get y equals plus or minus 1. So again, what that means is that that's actually two scenarios, two coordinates. If we say x is 0, then y could be either 1 or negative 1. So if x is 0, y could be either 1 or negative 1. And that's what generates the 2 points. That's how you go from one solution generating two solutions, because at some point you did a square root, getting a plus or minus, and those are the 2 points that are above and below. So now we still have to do the, let's say x is 2. So now this solution, if I say, let's say x is 2, then that would give me 2 plus 2y squared equals 2. And moving the 2 over, we get 2y squared equals 0. And dividing off the 2, we get y squared equals 0. And when you square root 0, you don't generate two possibilities. Plus or minus 0 is still just 0. So that means that if x is 2, y is only 0. So if x is 2, y is only 0. Those are our 3 solutions. Knew we expected. So that's how we solve a nonlinear system. The last 2 questions in your packet are interesting. I think they'll show up in more. I don't know that I'll necessarily include one in your exam. But it says, let's solve a system of nonlinear inequalities. So let's just look at the graphs and think about what it means. So in this first graph, I plot them here, we have x squared minus y squared is less than or equal to 1. Now look at that. What does that mean? In this particular graph, x squared minus y squared is less than or equal to 1. What does all that shaded region mean? Yeah, it means it's true. So if I choose any coordinate at all from the green region and plug it into this inequality, it should be true. Let's make sure we really understand what that's saying and choose a coordinate. I'll choose the coordinate 1, 2. I'm going to choose the coordinate 1, 2, just to see if it's true. But if I plug that coordinate in to x squared minus y squared is less than or equal to 1, then the equation is true. So if I plug in right here 1 squared minus 2 squared is less than or equal to 1, and 1 minus 4 is less than or equal to 1, and that's negative 3 is less than or equal to 1. So is that true? Yeah. So any coordinate from the green region will make that inequality true. What is, well, yeah. So now our second inequality is x squared plus 4y squared is greater than 4. Now let's just look at that. So that means that for that inequality, any coordinate outside of the ellipse will make that inequality true. So what we're looking for is which region in space is being shaded twice? Which region is being shaded by both purple and green? And this is what I'd like you to draw on your graph. It can just be a simple, quick sketch. It doesn't have to be overwhelmingly accurate, but draw an ellipse and then draw 2 hyperbolas. So it kind of looks like the markings on a basketball or on a baseball. And what we're interested in is this region. That region right there is inside the hyperbola, but it's outside of the ellipse. And so now if we choose any coordinate from within that shaded region, both inequalities will be true simultaneously. You know, it'd be worth trying once. You know, like what's a coordinate that's outside the ellipse but inside the hyperbola? We can still choose the coordinate 1, 2. So I already checked 1, 2 on the first inequality. Let's check 1, 2 on the second inequality. So x squared plus 4y squared should be greater than or equal to 4. If I plug in 1 squared plus 4, 2 squared, is that greater than or equal to 4? That's 1 plus 2 squared is 4. 4 is 16. And sure enough, 17 is greater than or equal to 4. So yes, any coordinate that I choose from this region or this region, both inequalities will be true simultaneously. And that's what we're talking about. You know how like when you go to a carnival and there's like a carny and they're like, pick any number, choose it. Wait, what is it that they say? What am I thinking of? Pick a card, any card. Yeah, there you go. Thank you, Josh. Yeah, I was a little off on the whole carny. So yeah, carnies, magicians, hey, you know, they're all show people. So that's what we're saying. When you shade something, you're effectively saying, pick a card, pick any card, pick a point, pick any point. That's what shading means. Whether the shading is on a number line, you know, all the time that we spent talking about, you know, shading number lines and turning it into interval notation, we're saying pick a point, pick any point, and those points will make the equation or inequality true. Okay, everybody, you can just scratch out number 2. This was just a demonstration so you could see what that looks like. All right, now we can move forward and look at chapter 9. Chapter 9 is about sequences. This is a very different type of chapter. There will be equations in this chapter, but what we're talking about is not a graph. Yeah, in fact, we're really not talking about a graph anymore at all. What we're talking about now is a concrete list of items. And looking at a concrete list of items, you either want the ability to predict the next item on the list, or you want to add up all the items in the list. And that's essentially it. But in chapter 9, I mean, there's a lot more that you can do with sequences. But you're looking at a list of items, and you either want to predict the next item on the list, or you want to add up all the items on the list. And those are the 2 skills that we'll be looking at. So I gave you a couple sequences up there to challenge you. So, and I know we kind of looked at it real quick the other day, but what would be the next item on the list for 1, 2, 4? What number could come next? 8. Yeah, it could be 8. Right? If we have 1, 2, 4, and if it is 8, what rule are you following in?
Double.
Doubling, right? So double, double, double. So 4 double would be 8, and then 16. But somebody else might have a different perspective. What number could come next there for 4? What did you say? It could be 6. What would be the rule if it's 6? Maybe now adding by 2. I mean, maybe the rule was start with the number 1 and then count to 2, but then after that start adding by 2 every single time. Maybe a slightly strange pattern because the pattern should be consistent all the way through. That you're using the same rule all the way through. So we shouldn't see a situation where we start with one rule that says add by 1, and then switch to a different rule, add by 2. But nevertheless, that's possible. You know, that could be somebody's pattern. What's another possibility? 1, 2, 4, what? What's another possibility that is following a consistent rule?
Seven.
Yeah, it could be 7. Why 7?
It goes up by 1, then it goes up by 2.
Yeah, because here you're adding 1, then you're adding 2, then you're adding 3, and then you'd be adding 4. So then consistent rule. You're saying each time you add 1 more than the last time. Other in fact, wouldn't it be? Oh, I guess we already said 8. Darn, I was going to say that's 2 to the 0, 2 to the 1, 2 squared. So then obviously the next number would be 2 cubed. But 2 cubed is 8, and that's the one way to look at. But still, that's a different way of looking at it. Okay, so with sequences, there are more than one way to interpret a sequence. So you could make the argument right up front that there's no one right answer. Unless you impose a rule that you're either talking about an arithmetic sequence, and an arithmetic sequence means that you're adding the same number over and over again. So in an arithmetic sequence, you get basic counting by sequences like 2, 4, 6, 8, 10, and you're adding by 2 every time, or 5, 10, 15, 20, 25, 30, you're adding by 5 every time. So by imposing a rule such as the sequence must be arithmetic, then you take away the possibility that there's infinitely many ways to interpret a sequence. There's just one way to interpret the sequence, and that is you're looking for what number are you adding over and over and over again. So likewise, the pattern could be, say, 10, 20, 30, 40, because every time you're just adding by 10. So those are arithmetic sequences. That's one type of sequence we'll study. The second type would be geometric. Geometric. And that means that you multiply by the same number over and over again. So if the sequence was 1, 3, 9, I'm going to start multiplying by 3 over and over again. So 9 times 3 is 27, times 3 is 81, times 3 is 243, and so on. So a geometric sequence, you multiply by the same number over and over and over and over again. So these are the two types of sequences we'll look at. And that way, there's definitely just one way to interpret the sequence, and everyone in the room will interpret the sequence in the same way. I did put up one bonus question up here, though. What's the next number in this sequence? This is a riddle. You'll definitely take it to your friends and family at the next party you go to. So what's the next number in the sequence? 1, 5, 10, 25. In fact, I'll even give you one more number, 50. What's the next number in that sequence? It is 100. Why 100? That goes times 5, that goes times 2, that goes times half, and then that goes by 2. It's not very consistent, is it? Why were you saying 100, Brandon?
I didn't say that.
Oh, Victor, why'd you say it?
Guess half, whatever. Not like 5 is half of 10.
Oh, 5 is half of 10.
Well, the first one half of them is
Yeah, it's pretty inconsistent. So this is a fun riddle because it's not necessarily a number pattern like what we were expecting. Rather, this is the value of coins in American currency. So you have a penny, nickel, a dime, a quarter, 50-cent piece, and then like a silver dollar, and so on. So maybe that was a bit of a cheap question. It's a riddle. It's supposed to be a little different. Okay, so on the one hand, we're talking about arithmetic and geometric sequences and how to predict what the next term is, but not just predicting what the next term is. Like after 5, 10, 15, 20, it's pretty easy to say what the next term is. The next term is just 25. What if I asked you for the 100th term? Okay, so I said, here's the sequence, 5, 10, 15, 20, and I want the 100th term. Well, that would be a little laborious if you actually had to sit there and count out, all the terms in order to get to the term you were interested in. So it'd be nice if there was a formula that could just immediately tell you what's the 100th term, or what's the 200th term, what's the 500th term. So we want the ability to predict the next term. We also want the ability to predict the nth term, whether n is the 100th term or the 200th term. Okay, so those are some skills we're looking for. And then the next question is, what is the sum of numbers? And these are two very interesting classic examples of finding the sum of sequences. Consider that first question there. 1 plus 2 plus 3 plus all the numbers going all the way up to 100. What is the sum of all those numbers? Or better yet, how could you find that sum? If I was going to pay you $10 to give me an accurate sum of those numbers, what would you do? Because I'm assuming you'd all do it for $10. I'm assuming. So how would you add up all those numbers? I mean, what would be one way you could do it?
add them one by one.
Yeah, you just add them all up one by one, right? You type it all in your calculator. Again, it'd be very laborious and time consuming to sit there and plug them all in. Plus, what are the odds that from 1 to 100, are you going to make a typo at some point? Maybe, Yes, you absolutely could. So what Chelsea's describing is the solution, not only for this problem, but for all arithmetic sequences. And the story goes, there's a mathematician, so just so you a little math history here, there was a mathematician, his name is Gauss, Carl Friedrich Gauss. And he was just a boy, so maybe a first grader in a kindergarten, or first grader in school. And the teacher wanted to leave the room for a bit, so she gave all the students in the room this problem, figuring they'll all sit there and be scribbling away, and it'll take them a good 10, 15 minutes to add it up, and that way the teacher could leave the room and go do something. So the teacher puts the problem on the board and is about to leave the room, and Gauss comes running up and says, oh, the answer is 5,050. And wait, is it 5,050? I think it's 5,050. The teacher, of course, thought that Gauss cheated or maybe already knew the problem, and in any case was annoyed because now this little boy is not going to be occupied and I can't leave the room. So then how did Gauss figure it out at such a young age? He used essentially the technique Chelsea was talking about. Like, Chelsea, I like yours because you just excluded the 100. Because then I think everyone can see that 1 and 99 is 100, and then 2 and 98 is 100, and 3 and 97 would be 100, and then you just have a whole bunch of 100s that you're adding up, and that's much easier. What Gauss did was he took the first and the last number. So 1 and 100 is 101. And then he took the second and the second to last number, 299 is 101. Then he took the third and the third to last number, which 398 is 101. And then how many 101s did he give? 50. So he had a whole bunch of 101s and he had 50 of them. So then he just did 101 times 50, and the answer was 5,050. So that's how we're going to add up sequences, is you'll essentially use a formula. In fact, here's the formula. The sum of n terms is you take the total number of terms and divide by 2. So there were 100 terms, divide by 2, that's 50. So there were 50 pairs. And what you do is you take the first term plus the last term, which is what we did. So A sub 1 represents the first term, A sub n represents the last term that you're interested in. And this formula of taking the total number of terms, divide by 2, that's the 50. And then add the first and the last term, that's the 101. And then you multiply, and that's the sum. Okay, so that's, again, it's just a little preview of what we're going to do. We're going to find the sum of the arithmetic sequences. But then we'd also like the ability to find the sum of geometric sequences. So take a look at the next sequence, 1/2 plus 1/4 plus an 1/8 plus a 16th. What does that add up to? And in fact, I'll go ahead and pull up. Who will do a better job? Maybe Desmos? Let's see. I type 1/2 plus, oh no, I'm not going to like that. Let's go to Google. Oh, I'll do that one right there. So 1/2 1/2 plus 1/4 plus 1/8. So watch what your totals are adding up to. So we started at 0.5, 0.75, 0.875 plus 1/16. Oops. 0.937 plus 1/32 plus 1/64 plus 1/128. So we're 0.9921 now. Plus 1/256 plus 1/512 plus 1/1024. So you can see where we're at right now, 0.999 something. We can keep going, plus 1/2048 plus 1/4096. So now we're at 0.999755. And what? Plus 1/4096, 8,192. So what are we approaching? We're approaching 1. Now, the philosophical question is the answer actually going to be 1 or just less than 1? This is a really good question in math. So what do you think? If I keep on adding up the terms, 1/2 plus 4 plus an 8, all the way up to infinity, okay, infinitely many terms, what is that sum going to approach? Is it going to approach 0.999999999 forever? Or is it going to be actually equal to 1? We haven't talked about this yet, have we? Okay. Yeah, so what do you think? If I keep on adding up those terms forever, and by that I mean genuinely forever, so you have to pretend in your mind that I'm just going to sit there typing in those fractions forever. Because obviously if I only did some finite number of them, then for sure we know the answer would be 0.99562, right? So if you only did finitely many terms, it's definitely going to be 0.999 and then 372. You know, it's going to end at the end there. But if you really did keep adding it forever, what will the answer be? This or this? Yeah, I mean, it would be very reasonable for you to say the top one. And so I'm going to give you 2 different proofs of this. In mathematics, we absolutely know that 0.99999 repeating, okay, another way of saying that is 0.999 repeating like that, is actually equal to 1. So, for sure, 0.999 repeating is actually equal to 1. And that might feel weird. Like you think I'm saying that to you while I wink. Like, hey, 0.999 is equal to 1. Like like we say it is, but it isn't really. But it actually is and really is. So let's consider that. First of all, what if I had a square? And so this is a geometric proof. The square, I'm going to start shading half of it at a time. I'm going to start shading half of it at a time. And so if I do start shading half of it at a time, first I shade in that half, then I'll cut this in half, then I'll shade that half. Then I'll cut this in half, and I'll shade that half. So that's essentially what I'm doing here in my sequence, right? I'm adding in half, and then half of a half, so that's 75%, and then half and a half and a half. So that was the, what, 83%? So if I keep on doing this, cut it in half and then shade it, will I eventually shade the whole thing? Like if I keep doing that forever? You might say, no, Mr. G. If you keep doing that forever, you're still just cutting a blank piece in half, and so there's still going to be a blank piece. But on the other hand, if I do that forever, then I claim that I will eventually shade every single point on the square. And that's a different way of looking at it. I claim that if I keep cutting it in half, shading it in, cut it in half, shade it in, I will eventually, so you choose any point on here, and I'll tell you that eventually I'll shade that point. So for instance, let's say I said, I will eventually shade that point. Because if you make the argument that you're not going to shade the whole square, then you must be able to choose a point that I'm not going to shade. So I tell you, go ahead and pick any point you like, and I say, I will eventually shade that point. Because I'll cut this in half and shade that. Then I'll cut this in half and shade this. Then I'll cut that in half and shade that. And then I'll cut this in half and shade that. And then, whoop, there, that's the time that I cut it in half and shaded it. So the argument would go that, yes, doing this process will eventually shade in the whole square. Because for any point you choose that you might say, no, it won't shade it in, you will eventually shade that point in. Okay, I realize I'm going on a little long here. We're talking somewhat about philosophy, but I want to make sure that we're all on board. So 0.999 really is equal to 1. So here's a couple different proofs for why that's true. Now, first of all, I really want to make sure. Do you believe it or not believe it? Like, here's the number 1. Where would be the number 0.99999? Would the number 0.999 be just to the left or at 1? What's your gut feeling about where 0.999 should be? You can either argue that it's the same as 1, or you would say it's just to the left. Right? And I think most people would say 0.999 is just to the left of 1. So like maybe it's right here. There's 0.999. So we need a way to convince ourselves, is 0.999 just to the left of 1, or is it actually at 1? So everybody try this with me. You've got a little room on your paper up towards the top, maybe go in the upper right-hand corner. And there's a really good mathematical technique for solving problems. I think we've done it before with logarithms. So let's just say that you have a number like 0.9999999. Oh, hold on. You have a number like 0.999, and you're wondering to yourself, what is that number? Is it equal to 1? Is it equal to something else? What is it? And a very valid mathematical approach to a problem is to say, I don't know what that is, so let it equal x. When you don't know what something is, let it equal x, turn it into an equation, and then you can manipulate it. So now that we have an equation, did everyone write this down? This is a really fun proof. You want to do it. This is part of your math culture. So we have an equation now, and that means we can manipulate an equation. What can you do to an equation? Anything you want, so long as you do it to both sides. So what we're going to do is multiply both sides times 10. If I multiply this side times 10, it moves the decimal once, so that becomes 9.99. And if I multiply this side times 10, it becomes 10x. So I wrote the equation above it, but the point is I took my equation, I said, okay, what's 0.999? I don't know, call it x. Now take the equation, multiply both sides by 10, so now I have 2 equations. And much like substitution or elimination, right now we can do elimination. We can subtract the 2 equations. So what happens if we subtract the 2 equations? Well, on the right-hand side, 10x minus 1x is just 9x. And on the left-hand side, what happens to all the infinitely many 9's? They all cancel out, and you're just left with 9. And then, of course, x is being multiplied by 9, so you divide by 9, and you end up with x equals 1. And so to the original question, what is 0.9999? 1. And that's a completely legit algebraic proof. There's another way to prove to somebody, you know, a friend or a neighbor or a family member, that 0.9999 really is equal to 1. Because I think there's a lot of resistance to the idea that it really is equal to 1. And that is simply add a third plus a third plus a third. So if I have a third, and a third, and a third, what is a third plus a third plus a third? What's a third plus a third plus a third? 3/3, right? And 3/3 is equal to 1, for sure. And yet, a third is 0.33333 repeating. And a third is 0.333 repeating. And a third is 0.333 repeating. And what is 0.333 plus 0.333 plus 0.333? 0.999, without a doubt. So for sure, once again, we see that 1 is equal to 0.9999. And this is not some sort of like weird thing in mathematics. Like we say it's equal, but it's like tongue in cheek. It just really is. So to the extent that you all know very easily that 1/2 is the same as 2/4, is the same as 3/6, is the same as 4/8. Like we have no problem at all saying that you can represent the same number by different fractional expressions. And it so happens that in math, you can also rewrite a decimal in 2 different ways. Oh, there we go. So in general, just like how many ways can you express a fraction? Infinitely many ways, right? You can take any fraction and express it infinitely many ways. How many ways can you express a decimal? 2 ways. And again, that's kind of funny. Fractions you can express infinitely many different ways. A decimal you can express in 2 ways. And so here's how. Let's say you take 25 cents. Okay, any decimal, but I'm just going to take a quarter. 25 cents is technically the same as 0.2499999. So those 2 decimals are equivalent. Just like 2/4 and 3/6 are equivalent. So it's a little mind-boggling at first to realize that decimals, any decimal can be expressed in 2 ways. One of them, you just have the normal last digit, and then the other one, you reduce that digit by 1 and tack on a trail of infinitely many 9s after it. So again, you can take any decimal number at all. It would be kind of funny actually if you were, getting older and you resisted being older. You could say, hey, I'm not 40, I'm 39.999. Right? You're a little sad about getting older. Okay, so sequences and series are pretty interesting. There's a lot to think about and a lot to talk about. All of that is just kind of a teaser about what is possible within this branch of mathematics, where the question is, if you're looking at a sequence, either by adding the same term or multiplying the same term, what can you find out? And what can you model? All right, so here we are. We're at the beginning of chapter 9.1. Let's go ahead and take a look at the notation. First of all the way at the top of the screen, all the way at the top, maybe above the 9.1, let's all agree how we're going to write out terms. And we're going to list our terms in the variable a with subscripts. So the terms would be a sub 1, a sub 2, a sub 3, a sub 4. And that's just how we're going to list out our terms. So in general, a sub 1 is the first term in your sequence. A sub 2 is the second term in your sequence. A sub 3 is the third term in your sequence. And a sub 4 is the fourth term in your sequence. So we'll always be using the letter A. Well, okay, to be fair, they'd use the letter A. Here they use the letter B. So it doesn't really matter. We'll, for the most part, use A. And furthermore, we don't just want the ability to think about concrete terms. We want to be able to think about just some term down there. Maybe the 100th term. If you skipped out quite a ways, you can say, okay, what's the 100th term? But you could go even further out and say, what's the nth term? And the nth term just represents any term you want depending on what number you're thinking about for n. So to a certain extent, a sub n is kind of like a function where you input a number for n, and that's the term you're thinking about. So if we wanted to talk about the nth term, the nth term is a sub n. And that gets to be whatever term you want it to be. So if you're talking about the 13th term, it'd be a sub 13, and you let n equal 13. There's one more thing that we'd want to be able to say, and that is, what's the term right after a sub n, and what's the term right before a sub n? So if we're looking at our sequence, and we're counting along, and we get to a sub n, what's the Exactly right, a sub n plus 1. And in math, in this topic, we would call it a sub n the nth term, and we'd call it a sub n plus 1 the next term. So if we're talking about the nth term, the next term is a sub n plus 1. And what about the term before the nth term? If we're talking about the nth term and we want the term right before it, what would it be? Yeah, a sub n minus 1. And we could call that term the previous term. It doesn't end there, of course. You could talk about what's the next term. And then you could look at the term a sub n plus 2. Or you could look at the term before the previous term, which would be a sub n minus 2. Anyway, this is how we refer to the terms in our sequence. So when we say the nth term, we're just referring to any given term. And when we look at the term after a sub n, we say a sub n plus 1. Okay, so that's our terminology. That's how we'll refer to terms in a sequence. Whether that sequence is arithmetic or geometric, we'll refer to it as a sub n. So let's look at how to simply write these things out. Like in number 1, they're saying write out the first 4 terms in the given sequence. So they're saying the formula for our sequence is a sub n equals 2 to the n minus 1. And they're specifically saying only for n greater than or equal to 0. So one more thing that's important to notice in sequences is our input value, right? The input number that we're going to plug in for n can only be whole numbers now, right? Whereas previously, if you had a function, if the function was just like 2x minus 3, you're allowed to plug in any number you like. You can plug in 5, or you can input 5.6, or you can input 5. You can input anything you want, including decimals and fractions. But right now, we're talking about sequences, so we're only looking at whole number n values. And specifically, they're saying that n starts at 0, and then you can plug in 0, 1, 2, 3, 4, all the way up to infinity. And that's your sequence. So let's go ahead and write out the first few terms. Again, n represents an input value. So if I input 1 for n, then that becomes 2 to the 1 minus 1, which 2 to the 1 is 2, 2 minus 1 is 1. So the first term is 1. If I input 2 for n, then that becomes the formula 2 squared minus 1. And 2 squared is 4, 4 minus 1 is 3. Or the third term, this is the work you'd show on your paper for this problem. We're just plugging in numbers for n. So the third term, I plug in 3 for n, so 2 cubed minus 1. 2 cubed is 8 minus 1 is 7. And the fourth term is 2 to the 4th minus 1, which 2, 4, 8, 16 minus 1 is 15. That's all the problem asked us to do, write out the first 4 terms. And so far, if you wanted to summarize your knowledge, you would say that my sequence is 1, 3, 7, 15, ... And that's the sequence defined by this formula. Now, that's just one way to write down a sequence using that formula. Number 2 gives another valid way that you might see it. And what they have now is curly brackets with n squared plus 1 over n plus 1, where they're saying, let n take on the values all the way. What?
Your number 2 is.
Oh, it is? Oh, no, that's not what I want to have happen. Oh, so I took out some problems from your list, folks. So you can just do the problems that I'm doing up here on the board. I apologize. I cut down, wait. Go back a second, unerase that. Let me see here. Well, I definitely want my page to match your page. No, I'm gonna make my page match your page. So in a minute here, when we take a break, I'll update my list so it looks like yours. So for now, let me just keep doing the problems you're doing. So everybody, let me get a packet. And let me look at number 2 with you. All right, so your number 2. It says curly bracket 5k minus 2, where k goes from 1 to infinity. So let's look at how to read that notation. In number 2, it says curly bracket, which means let's look at the set of numbers of the form 5k minus 2, where we're only going to allow k to equal 1 all the way up through k equals infinity. So you kind of read it from bottom to top. You say, I want all the numbers of the form 5k minus 2, where k can be any integer between 1 and infinity. So if we let k equal 1, then the first number of the form 5k minus 2 would be 5 times 1 minus 2, which is just 5 minus 2, which is 3. So 3 is a number of the form 5k minus 2. It's a multiple of 5 minus 2. Likewise, if we let k equal 2, then we'd have 5 times 2. Again, that's a multiple of 5 minus 2. 10 minus 2 is 8. And then if we let k equal 3, then 5 times 3 is 15, minus 2 is 13. If we let k equal 4, then 5 times 4 is 20. That's a multiple of 5 minus 2, and that'd be 18. So that's what that notation means. We're saying, look at the set of all the numbers of the form a multiple of 5 minus 2, where we're starting with the first multiple of 5, which is 5. So our set then, our set of numbers would be the numbers 3, 8, 13, 18. Then you just keep going, multiples of 5 minus 2. So 25 minus 2 is 23, 30 minus 2 is 28, and so on. So that set is the set of multiples of 5 minus 2. That's what that would look like. So then your number 3, I want the set of numbers of the form n squared plus 1 over n plus 1, where we allow n to take on the values from 0 to infinity. Now I admit, math notation is a little arbitrary, isn't it? Like this whole notion of putting a little n equals 0 at the bottom and then infinity at the top, like why didn't they choose to do 0 at the top and infinity at the bottom? Well, that's just notation that has come down to us through the years. So this is just what the notation means. So again, now we would go through and start plugging in 0, 1, 2, 3, 4, and seeing what that function represents. So if we let n equal 0, we get 0 squared plus 1 over 0 plus 1, which is just 1 over 1, which is 1. So the first term is 1. If we let n equal 1, then we'd have 1 squared plus 1 over 1 plus 1, which is 2 over 2, which is also 1. So that's kind of interesting. The first 2 terms in the sequence are 1 and 1. And if that's all you had so far, if I was like, hey, what's the next number in the sequence? I mean, yeah, you don't have much to go on, right? I mean, probably you would just say 1. I heard a couple of you guys that like, I don't know, what else could it possibly be? I mean, it looks like this is just going to be a sequence of 1s. And yet, when we go ahead and plug in the next term, so n equals 2, that'd be 2 squared plus 1 over 2 plus 1. That's 4 plus 1 is 5 over 3. You get the number 5/3. I don't think anyone would have guessed 5/3. And then likewise, we have n equals 3. So 3 squared plus 1 over 3 plus 1. 9 plus 1 is 10 over 4, which simplifies to 5 halves. Oh, even more counterintuitive. And yet, this is a well-defined sequence. It's not an arithmetic sequence or a geometric sequence, because you're not adding the same number every time. Like here, I added nothing, and then here I added 2/3. And then here, golly, to go from 5/3 to 5 halves, I think I actually subtracted some. Yeah, I actually subtracted 0.16. So it's definitely not an arithmetic sequence or a geometric sequence, but it's a sequence nevertheless. And it's defined by this formula. All right. So all of that so far, these first 3 formulas that you just looked at, go ahead and label them explicit. These are explicit. Not like the lyrics on a Tupac album. Explicit would mean that he's using potty language that you shouldn't let your toddlers listen to. Explicit in this case means it's spelled out. which I suppose, as is Tupac's language, spelled out for you. Leaves nothing to the imagination. But what we're saying here with explicit is, in an explicit formula, you can calculate any n value directly. Now just imagine the power here. So if I want to know the 100th term in this sequence, I don't actually have to list out the first 99 terms in order to get to the 100th term, right? That'd be real laborious. I don't have to sit here and list out the first, second, third, fourth, fifth, all the way to the 98th, 99th, 100. Like I don't have to spend all that time. I can just go ahead and plug in n equals 100. And so that's what explicit means. I can just immediately say 100 squared plus 1 over 100 plus 1. And that gives me 1, 0, 0, 0, 1 over 1 over 1, which I don't know if that reduces in any way. But explicitly, I can just immediately know what it is. Did I do that wrong? Oh. So that's what explicit means. The next couple of formulas are called implicit. So the next couple, which already my mind is reeling just trying to think of what would that even mean if there was a musical album, like a CD produced by an artist, and they're like, warning, implicit lyrics. Like they don't use any bad language at all, but it's implied. Anyone? No? Would anyone like to listen to a musical album where the lyrics are implicit? Okay, never mind. Maybe it's just me. So implicit means that you actually have to calculate every single term to get to the next one. So you have to calculate all in order. Okay, and to that extent, it's kind of like climbing a ladder. So if you're climbing a ladder is implicit because you cannot just suddenly and spontaneously jump up to the 20th rung on the ladder. If you want to get to the 20th rung on the ladder, you have to climb every rung on the ladder until you get to the 20th one. And so that's implicit. There is no skipping ahead. You just have to go doggedly in order. So let's look at this first one. It says if A1 is 3, that means the first term is 3. And we have a formula, which is A sub n plus 1 equals A sub n minus 1. And they're saying that that's true for all n values, all whole numbers starting at 1. So what numbers can I plug into this formula? 1, 2, 3, 4, 5, 6, 7. Now we'd like to know what is this sequence. So underneath this, I would put in English that A sub n is the nth term, and A sub n plus 1 is the next term after the nth term. So how does this work? You will have to write down each equation to get to the next term. So we already know A sub 1. How do I get A sub 2? Well, A sub 2, according to this formula, A sub 2 would be equal to A sub 1 minus 1. Now that's one way to look at it. Okay, I want A sub 2, so I take the term right before it, which is A sub 1, and subtract 1 from it. And that would mean that if I'm plugging in the first term, which is 3, that's 3 minus 1, and the answer is 2. So the first term was 3, the second term is 2. Another way to look at it, other than just bumping that number down 1, is to literally start plugging in n values. So if I have A sub n plus 1 equals A sub n minus 1, the first thing I do is start plugging in n values, and it says I can only plug in n values starting at 1. So here, if I plug in 1, that would be A sub 2 is equal to A sub 1 minus 1. Now let n equal 2. So if I plug in 2 right now for n, that'd be A sub 3 equals A sub 2 minus 1. Maybe I should write that out. Let n equal 1. Let n equal 2. So the next one would be let n equal 3. So if I plug in 3 for n, that'd be A sub 4 is equal to A sub 3 minus 1. So what I hope you see from this is I'm listing out my formulas for the second term, the third term, the fourth term, and each formula is written in terms of the term in front of it. So I only know the fourth term if I know what the third term is. So now I can start plugging in all my numbers. So to get the second term, I need to know the first term, which they told me. So that was 3 minus 1, which is 2. To get the third term, I need the second term, which I just calculated was 2. So I'd plug in 2 minus 1, which is 1. To get the fourth term, I need the third term, which I just calculated. So I plug in 1 minus 1 equals 0. And to get the fifth term, I need the fourth term, which I just calculated, which was 0, to be 0 minus 1, which is negative 1. This is referred to as an implicit formula. You can only calculate the next term, a sub 6. Like, in fact, let me just go down the line. What if suddenly I wanted to know what the 100th term was? I can only calculate the 100th term if I already know what the 99th term is. So, see, this implicit formula is a little unhelpful, because if I want the 100th term, I would first have to know what the 99th term is in order to subtract 1 from it in order to get the 100th term. So that's what we refer to as an implicit formula. The next one, which they're writing out in terms of b, so they're saying the first term is 2, and now they're saying b sub k plus 1 is equal to b sub k, no, 3b sub k plus 1, only for k values starting at 1 and going up. So again, notice what they're saying is, they're saying to get the next term in the sequence, you have to know the previous term in the sequence, triple it and add 1. So if right now I wanted the 98th term in the sequence, if right now I wanted the 98th term in the sequence, I would have to first know the 97th term in the sequence in order to calculate it. So it's kind of inconvenient. What if you don't know what the 97th term in the sequence is? You'd be kind of stuck. So instead, you just have to start at the beginning. And you'd say, let k equal 1. So the first thing would be b sub 2 is equal to 3b sub 1 plus 1. And since they told me what b sub 1 is, I can start the process off by plugging in a 2 there. So then 3 times 2 plus 1 is 6 plus 1 is 7. And then if I let k equal 2, then my third term, and again, I'm just plugging 2 into this formula. 2 plus 1 is 3. So b sub 3 is equal to 3b sub 2 plus 1. And I know what b sub 2 is because I just calculated it. It was 7. So I would say 3 times 7 plus 1 is 21 plus 1 is 22. What if we just listened to old 80s dance music the entire time we did mathematics? Would that add to your experience or take away from it? It would add to it? All right, some of you are excited, some of you maybe not. Okay, so again, if k equals 3, then the next term would be b sub 4 equals 3b sub 3 plus 1. And so I know what the third term is. I just calculated it, so it'd be 3 times 22 plus 1, which is 66 plus 1 is 67, and so on. Now, let's keep in mind the instructions for this whole section was write out the first 4 terms in the given sequence. So I think I already had it. B1, B2, B3, B4 is the sequence 2, 7, 22, 67. So that's the sequence generated for number 5. All right, we have 2 more, and then we'll take a break. So number 6, you got the first term is 117, that sure is arbitrary. And then the n plus first term is 1 divided by the nth term. So consider trying to phrase this in an English sentence to someone. To get the next term, take the previous term, then do the reciprocal. That's it. To get the next term in the sequence, take the previous term and do the reciprocal. Or do 1 divided by the previous term. So let's see what that would look like. If I let n equal 1, then I have a sub 2 equals 1 over a sub 1. So the second term is the reciprocal of the first term. Likewise, if I let n equal 2, then I'm saying a sub 3 equals 1 over a sub 2. The third term is the reciprocal of the second term. If I let n equal 3, then that's a sub 4 equals 1 over a sub 3. So we're saying the fourth term is the reciprocal of the third term. It's really helpful to practice verbalizing things in sentences. Because if you can describe it to someone else, then your brain can understand it better. So all the way up then, the fifth term is the reciprocal of the fourth term, and in general, the n plus 1 term is the reciprocal of the nth term. So what does this sequence look like? My first term is 117, so my second term is 1 over 117. And then my third term is 1 over the second term. Well, what's 1 divided by 1 over 117? Looks weird at first. 1 divided by 1 over 117. First of all, if you just use the rule, the verbal rule, recall the third term is the reciprocal of the second term. The fourth term is the reciprocal of the third term. The fifth term is the reciprocal of the fourth term. And reciprocal only ever just means flip it. So if the second term is the reciprocal of the first term, and the first term is 117, then the reciprocal of 117 is 1 over 117. If the third term is the reciprocal of the second term, the reciprocal of 1 over 117 is just 117. So again, you're just going to be flipping the numbers. But if you wanted to prove to yourself, what is 1 divided by 117? That's really 1 divided by 1 over 117. And dividing by a fraction is the same as multiplying by the reciprocal. And 1 times 117 over 1 is just 117. So what does this sequence generate for us? The fourth term is just the reciprocal of the third term, so that's 1 over 117. And the fifth term is the reciprocal of the fourth term, so that's 117 again. And this turns out to be a fairly silly sequence that just goes 117, 1 over 117, 117, 1 over 117, and so on. Now this sequence is not arithmetic. Same number every time. It demonstrates what an implicit formula looks like, where you have to calculate each term to get to the next one. And by the way, folks, go back to where you wrote the word implicit. Another word for implicit is recursive. Recursive. That sounds like to write something in cursive again. Yeah, I don't have a lot of practice in cursive. There we go. Recursive. But no, what that means is to recur. So to recur over and over again means that the formula is recurring, meaning in order to calculate the next term, you have to know the previous term. Okay. Well, we have one more question, which is on the next page. And this is a classic formula. I wonder if you ever wonder what I mean by when I say things like classic. This is a classic formula. Oh, this one's famous. I mean, this formula we're about to see is like the Mona Lisa of formulas, right? I mean, you all know what Mona Lisa is. It's just some painting by who? Leonardo DiCaprio? No. Leonardo da Vinci. And it's in the Louvre in Paris. So the Mona Lisa is a classic. This formula is also a classic. This formula, go ahead and label it, is called the Fibonacci sequence. Fibonacci is kind of a big deal. He was a mathematician who lived in the 1200s, and he actually brought and popularized the decimal system to Europe. So before Fibonacci wrote his book, all of Europe was still using Roman numerals. And just so you can all appreciate Roman numerals, I mean, I think you all know Roman numerals, or you've seen them before. That's the number 1, and that's the number 2, and that's the number 3, and that's the number, no, other way. Here's the number 4, and then here's the number 5, and then 6, and then 7, and then 8, and then 9, and then 10, all right? So there's the Roman numeral system. And so just imagine even the challenge of adding 8 plus 12. Yeah, I mean, you kind of just have to think about each little bit. Like, well, that's 1, 2, 3, that's 5, so I've got a V, and I was another V, and then that, but 2 V's make another X, and so I've got 2 X's, and so there, the answer is 20. But anyway, it's weird and it's awkward. So I want you to appreciate that before the 1200s, this is what Europe was doing. This was what everyone was doing. You know, kings, queens, monks, nuns, anybody was anybody, they were doing math in Roman numerals until the 1200s. What? Okay, so Fibonacci wrote his book and he popularized it. It wasn't like really securely rooted in Europe until more like the 1400s or the 1500s when everybody was using it. Isn't that wild to think that just 500-600 years ago people were using the Roman numerals? Does anybody care? It's weird. Folks, that's weird. Could you imagine if we were still doing the Roman numerals? We wouldn't know because it would just be normal. Could you imagine that maybe 500 years from now in the year 2500, they're going to use a different number system? And they're going to look back on us and be like, can you believe they're still using the Arabic numeral system? That's so weird. I mean, gosh, what was it like to be them? What number system would they be using? We don't know. We can't even fathom it because we're still using our number system. Okay, so 1200s, Fibonacci comes along, writes a book, popularizes the decimal system. Okay, so the decimal system using the Arabic numerals. That's what we use today. The decimal system using Arabic numerals, not Roman numerals. And so Fibonacci, among other things, has a problem about rabbits. Well, let's do the sequence first. Okay, everyone, let's do the sequence. Everyone start by just writing down 1 and 1. The Fibonacci sequence is this. Take the previous two terms and add them together. So 1 and 1 is 2. Keep going. Take the previous two terms and add them together. 1 and 2 is 3. Take the previous two terms and add them together. 2 and 3 is 5. Take the previous two terms and add them together. 3 and 5 is 8. Take the previous two terms and add them together. 5 and 8 is 13. Take the previous two terms and add them together. 8 and 13 is 21, and so on. This is named after Fibonacci because he popularized it in a book. The book, in which he brought the decimal-based, Arabic numeral-based.
Well, he also talks about the Fibonacci sequence being present in almost all of life.
Yeah, absolutely. So folks, I mean, if you're going to do anything today other than eat, live, breathe, and sleep, go home and go to YouTube. And I think someone who does a really fine job of this is the mathematician. It's a girl. Does anyone know her name? She's pretty fun. I enjoy watching her videos. She's very energetic. Oh yeah, here she is. What's her name? V Hart. That's right, V Hart. How am I going to get this volume turned on? So V Hart, that's her name. She does a really good job of describing a lot of fun mathematical ideas, and she does it in this kind of animated way that you can tell. I mean, it's a little spastic, like as you watch it, you know, it moves around a lot. But she does a really good job of drawing and describing. She's pretty funny. Oh, there she is.
Or if you want to drop some mistakes, you can start with a
Now, did I even? Oh yeah, doodling and math. So this is Spiral's Fibonacci sequence. This is video 1 of 3. Definitely entertaining. Everybody go home and watch this. During it, she's going to talk about the Fibonacci sequence and how the Fibonacci sequence, oh, there it is again. So there's the Fibonacci sequence. And what she's describing in here is that there's all sorts of natural living systems that appear to have these numbers show up in the sequence. Okay, well, again, I'm not going to have us watch the whole thing, but she's showing the various spirals that you see. Okay, I'm just going to stop, because again, I'm not going to show you the whole thing. But you go home and you watch it, because it's pretty entertaining and fun. So there's V Hart. What else do I want to say about this? Fibonacci, watch the video. Oh, that's what it was. I wanted you to actually see it. So Fibonacci problem about rabbits. Folks, I realize I might look like I'm just up here rambling. Everything I'm telling you right now is really important. Okay, and I'm bringing it all together. This is fun. You're going to really like this. So here is Fibonacci's. This is one problem that Fibonacci had in his book that popularized the Arabic decimal system in Europe. Let me see if I can. I was hoping it would actually show. So Fibonacci sequence first appears in the book Liber Abaci in 1202. And it describes a group of rabbits starting from a single pair of rabbits, and they start having kids. And what happens as that pair of rabbits becomes of mating age. So now that they can mate. And then once they do start having kids, those kids grow up and then they can have more rabbits. And then you're starting and you're watching this family tree of rabbits as they continue to produce more and more and more rabbits. I think what I'll do instead of that little table right there is let's go to YouTube and actually see Fibonacci rabbits. What's going to be a good one? Maybe this one? Ah, Gresham College, can't go wrong. That is provided it's actually going to describe it.
Also, I mentioned Fibonacci.
Nope, he's not really describing it. This one.
Hey man, fans, Jason Marshall here with a special look at the solution to Fibonacci's rabbit problem from mat150 episode 16. Here's Fibonacci's question. If two newborn rabbits are placed in a pen, how many rabbits will the pen contain after 1 year?
Okay, so that's the question. That might not be word for word what was in his book. But first of all, just consider what a strange and interesting thing this is. Is anybody going to take two rabbits, put them in a pen, and then just wait? I mean, unless you're a rabbit farmer. I suppose if you're a rabbit farmer and you're like, let's breed some rabbits. But that's essentially what Fibonacci is asking is how many rabbits would there be and how would that mating appear?
To answer his question, Fibonacci wanted us to assume that rabbits always produce one male and one female offspring, that they can reproduce once per month, that they can start to reproduce when they are 1 month old, and that rabbits never die.
Okay, so obviously this makes a lot of assumptions that aren't even real, right? Because first of all, even if one parents of rabbits produced a male and a female, should they be mating? Probably not. They're brother and sister. So this whole experiment would go downhill pretty quickly. But this is just the mathematics of the problem of potential reproduction. Okay?
So that's the question. What's the solution? Well, let's think in terms of how many pairs of rabbits are in the pen at the beginning of each month, starting with the one newborn pair in the pen at the beginning of the first month. These newborns are too young to reproduce, so we begin the second month with one pair as well. It's the same pair, but they're now adults that are mature enough to mate. As a result, one new pair of rabbits is born at the end of the second month. So
notice how helpful this is that they're showing the tiny rabbits, meaning they're not old enough to mate yet, and then the larger rabbits, meaning they are now capable of mating.
the original pair again mates at the beginning of that month, but the newborn pair does not. The original pair produces another pair of offspring. So at the beginning of the fourth month, we have a total of 3 pairs of rabbits. The original pair, their newest offspring, and their first pair of offspring, which are now adults. 2 pairs can now mate, and they each produce yet another new pair, giving a total of 5 pairs at the beginning of the 5th month. Now,
Do you follow where all those rabbits are coming from? I wish I could write on this. So these were immature, couldn't mate. They grew up, now they can mate. So this is that pair, and they just had babies. Now they continue forever. They're going to keep on having babies. So they just had that pair of babies, and that pair of babies. Over here now, this pair of babies isn't old enough yet. Now they got older. Now they can start mating. And so now that is that pair still mating, and they just had babies. Okay, that's probably as far as we need to go with the video. Do you see the numbers that they're producing? 1, 1, 2, 3, 5. That is the Fibonacci sequence. And so this was the math problem in his book. Let's see if I can actually find it. No. Whoa. You there, Apache? It'll be here. Oh, I think. Yeah, this is it. So this is the actual passage. Wait, is that really the actual passage? I don't want to dispute it. It's not. Boy, why is it so hard to find a quote from a book written in the 1200s? The infamous rabbit problem starts at the bottom of 283. Oh, but they don't even, oh man. I should have found this before it came in. All right. Well, I'll look for it over the break. Okay, so let's just finish our problem and then I'll look for it over the break. So everyone, here's our last question. It was about the Fibonacci sequence. Let's actually calculate it now using the recursive formula. So it was, we're saying, notice now we're using F out of honor for Fibonacci. So the 0th Fibonacci term is 1. The the 0th term is 1. The first term is 1. And now they're saying that the formula is F sub n equals F sub n minus 1 plus F sub n minus 2. So notice what that formula is saying. It's saying that if you want the nth Fibonacci term, you need the previous Fibonacci term plus the previous Fibonacci term. And this is a way of saying add the two previous terms together. So now that I have the 0th term and the first term, I want the second term. So this is unfortunate that they number it with 0, 1, and 2. The 0th term is this, and the first term is this, and then so the second term is this, even though it's the third term, they're calling it the subscript 2. So f sub 2 is really f sub 1 plus f sub 0, which you can tell the effect is that the next term is the sum of the previous two terms. So that would be 1 plus 1, which is 2. So then the third term, which is subscript 3, is f sub 2 plus f sub 1, which f sub 2 was actually 2, f sub 1 was 1, so 2 plus 1 is 3. And so forth. F sub 4 would be f sub 3 plus f sub 2. And f sub 3 was 3, f sub 2 was 2, and so that next number is 5. Okie doke. Time is 9:20. Let's all be back at 9:30. All right. What I have on the board now matches what you have on the board, and we're done looking at just using formulas to generate a sequence. So where does that put us? We're about to look at, oh no, why is that? Okay. Yes, for now we're about to look at number 8. Now, just to wrap up that previous idea, so first of all, I couldn't find the quote. I couldn't find the actual quote by Fibonacci in his book from the 1200s. I just wanted to find the problem where he talked about the rabbits. I couldn't find it. So I'll keep looking for it, but I wanted to share with you. Now, first of all, are you folks familiar with the phrase breeds like rabbits?
Yeah.
Have you ever heard that? And what does that mean? Right, like rabbits breed very quickly. So, I can only imagine that this was known even to Fibonacci and the people of his time, and that's why he chose rabbits as the subject of his question. Now, the other thing that is fun, again, this is Mickey Mouse's Fantasia Noah's Ark scene. I think this is it. Oh, I have to open the screen again. All right, here we go. So, did you all see, well, maybe you did, maybe you didn't. There's, at Disneyland, this thing called Fantasia. Are you familiar with it? So, basically, Mickey Mouse, it does this whole classical music scene. They show it at Disneyland late at night, and they play a bunch of music, and they have a show of a video like this. And Mickey Mouse. Well, all sorts of things happen. So I'm just not sure if you're familiar with it or not. But there's this one particular scene where they even go through and they do Noah's Ark scene. So they, Noah grabbing all these animals, two of each animal, bring it onto the ark. Then at the very end, there's this piece of humor that is wildly funny if you understand the math behind it. And so here's Double Duck, and all the animals are leaving. So just watch. Two of each. Huh? Huh? You see? Let's go back. I'll go back here. Hilarious! Right? Two of each animal goes on the ark, but then who leaves like dozens and dozens of rabbits? Okay, well, whether you enjoy, maybe you enjoyed all that, maybe. All right. So then let's continue on. So we've seen how to use these formulas. Now what we'd like to do is each term after the first term different. Very good. Okay, in number 8, 9, and 10, it says determine if the given sequence is arithmetic, geometric, or neither. So if it is arithmetic, find the common difference, and if it's geometric, find the common ratio. So let's go ahead and define those terms. Let's just say that you had the simple sequence 5, 10, 15, 20. This is an arithmetic sequence, and what you're adding by every time is 5. And so we would say D equals 5. So the common difference is whatever you're adding by every single time in an arithmetic sequence. Whereas if you had a geometric sequence, like say 1, 2, 4, 8, 16, then this time what you're doing is you're multiplying by 2 every single time. And so we would call that the common ratio. Common ratio. And we denote that by the letter R in a geometric sequence. So in this next section then, they simply want to know, is it arithmetic? If it is, tell me what D is. And if it's geometric, tell me what R is. And if it's neither of those, then you can just say neither. So in number 8, we would look at it, and what you probably want to do is just calculate the first few terms. So at number 8, we're looking at numbers of the form 3n minus 5. So that's a multiple of 3 minus 5. And we're starting from n equals 1. So you could probably just do this in your head, or you can write down the work. But if I let n equal 1, and notice also that you could do a table of values. You could just do a table of values to start generating your sequence. So that could be your n value, and then you're looking at 3n minus 5. And we're starting at the numbers 1, 2, 3, 4. So if I have to start plugging in, so that's 3 minus 5 is negative 2, 3 times 2 is 6 minus 5 is 1, 3 times 3 is 9 minus 5 is 4, 3 times 4 is 12 minus 5 is 7, and so on. Maybe one more number. 3 times 5 is 15 minus 5 is 10. And what's happening in this sequence? I realize I'm writing it differently now. I'm writing it as a table of values instead of writing it sideways. If you wanted to write it sideways, you could. The sequence is negative 2, 1, 4, 7, 10. What are we doing every single time? We're adding by 3. So here we added by 3, and here we added 3, and here we added 3, and here we added 3. So indeed, the common difference is 3. So to answer this question, you would say the sequence is arithmetic, and D equals 3. And number 9, I'd probably make a table of values again. I'm saying I'm looking at the set of all numbers of the form 3 times some multiple of a fifth. Not a multiple of a fifth, but a power of a fifth. So I'd probably start writing it out. So I know that I'm starting with n values of 1. And I want to calculate 3 times 1/5 to n. Or to the n minus 1. So I would start plugging those things in. So that'd be 3 times 1/5 to the power of 1 minus 1 is 0. And then this would be 3 times 1/5 to the 2 minus 1 is 1. And then 3 times a fifth power of 3 minus 1 is 2. And that's 3 to the power, or 3 times 1/5 to the power of 4 minus 1, which is 3, and so on. So you can see the shape of all the numbers. And then you would want to actually simplify all of those. You could write them down as fractions. This first one would be 3 over 1 times, well, anything in the power of 0 is just 1. So that's just a fraction of 3 over 1. Whereas this next one is 3 over 1 times 1 over 5. So that's the fraction of 3/5. And this next one is 3 over 1 times 1/5 squared is 1/25. So you would say that that fraction is 3 over 25. The next one, 3 times 1/5 cubed, so that's 3 over 1 times 1 over 5 cubed, which is 1 over 125. And so we have 3 over 125. The next one is 3 times 1/5 to the 4th, so that's 3 over 1 times 1 over 5 to the 4th. That's 525, 125, 625, so 1 625, which is 3 over 625. So that's what our sequence looks like. And again, it might be helpful to write it out sideways. So our sequence is 3 over 1, 3 over 5, 3 over 25, 3 over 125, and so on. So what are we doing to get from one term to the next? Are we adding a number over and over again? Or are we multiplying a number over and over again? No, we are multiplying over and over again. What are we multiplying by? Yeah, well, in the denominator, certainly we are just multiplying by another 5. To get from 3 over 1 to 3 over 5, what do you technically, do you do anything to the numerator? Does the numerator change from one term to the next? The numerator is not changing at all. It's the denominator that's changing. What are you multiplying by in the denominator? You're multiplying by 5. So to get from this term to this term, you multiply by 1/5. And to get from this term to this term, you multiply by a fifth. And to get from this term to this term, you multiply by a fifth. And to get from that term to the next term, you multiply by a fifth. And so each and every time you're multiplying by 1/5. And therefore, your common ratio is 1/5. So this is a geometric sequence because you're multiplying over and over again. And the ratio that you're multiplying by is 1/5. And in fact, that's kind of obvious from the formula, because what you have is 3, which is just a constant number 3, being multiplied by 1/5 over and over and over again, depending on the exponent. So the 1/5 right there, the number that you see, that is the common ratio. You can frequently build a fractional common ratio by just looking at the numerator and denominator separately and just asking, what are you multiplying by every time? So in the numerator, what am I multiplying by every time? Just times 1. You know, 3 times 1 is 3, 3 times 1 is 3, 3 times 1 is 3. So the numerator of my common ratio is 1, because in the numerator, I'm just multiplying by 1 over and over again. Whereas in the denominator, what am I multiplying by over and over again? 5. So the denominator would be 1, or the denominator would be 5. So let's try another fractional problem like that. And number 10, they're asking, what kind of sequence is it? We don't know yet. But it goes 1/3, 1/6, 1/12, 1/24. And just going into a sequence, you don't know if you're adding something over and over again or multiplying over and over again. But you could go with your first guess. What does it look like we're doing? Yeah, what are we multiplying by?
1/2.
Yeah, 1/2, because in the top, you're multiplying times 1, times 1, times 1. But in the bottom, you're multiplying times 2. So 3 times 2 is 6, times 2 is 12, times 2 is 24. And so your common ratio is simply 1/2. Over and over and over again, you're multiplying by 1/2. So it is a geometric sequence, and the common ratio is 1/2. So about number 11, we have 17, 5, negative 17, negative 19. So with every sequence that you look at, you want to ask yourself, am I adding the same number over and over and over, or am I multiplying the same number over and over? So first of all, is multiplication really on the table? Not really. I mean, what do you multiply times 17 to get 5? And then what do you multiply by 5 to get 17? And what do you multiply by negative 17 to get negative 19? Really doesn't, nothing comes to mind. Whereas what am I actually doing in terms of adding and subtracting? To go from 17 down to 5, I'd have to subtract 12. And to go from 5 all the way down to negative 17, I'd have to subtract 22. And to go from, did I write that down wrong? I did. Oh no. Scratch that. I went from 17 to 5 to negative 7 to negative 19. Okay, that looks much better. The previous one didn't have a solution. So to go from 17 down to 5, I subtract 10. So to go from 5 down to negative 7, I subtract 12. And to go from negative 7 down to negative 19, I subtract 12. Okay, so that looks promising. This is an arithmetic sequence. Because every time I'm subtracting 12. Or you could say every time I'm adding negative 12. So in this case, this is arithmetic. And D equals negative 12. What about this next sequence? 2, 22, 222, 2,222. Are we adding something over and over, or are we multiplying something over and over? What are we multiplying by? Oh, now you could say times 11. In the first case, that worked. 2 times 11 is 22. But what's 22 times 11? 242. Really close. That was a good guess. Is there anything we're multiplying by over and over again? Addition, it might be a little easier because let's talk about both. How do I know what I'm adding every single time? It could be tricky to do it in your head. Like from 2 to 22, what did we add? 20. But if you're not sure what you're adding every time, what you do is you take any term and subtract the one before it. So that's the rule. If you want to know what the common difference is, you take any term and subtract the term in front of it. So the common difference, 22 minus 2 would be 20. And then 222 minus 22 would be 200. And then 2,222 minus 222 would be 2,000. So no, I'm adding 20, adding 200, adding 2,000. This is not an arithmetic sequence because I'm not adding the same number every time. So how do you know what the common ratio is? It goes the same way where you take any term and divide it by the term in front of it. And that would tell you what you multiplied to get from one to the next. So 22 divided by 2 is 11. But then 222 divided by 22 turns out to be a weird decimal. Yeah. If you actually do it on a calculator, 222 divided by 222 divided by 22 is 10 times 10.09 repeated. So no, and if I keep trying and I say take this number divided by that one, 2222 divided by 222, then we're multiplying by 10.009. So no, it's not geometric either. We're not multiplying by the same number over and over again. But let's formalize that now, this idea that we just talked about. If you'd like to find the common difference, so the common difference, D, is equal to any given term minus the term in front of it. So notice how I wrote it down. If you want the common difference, just take any term and subtract the term right in front of it, and it should always give you the same number. If you want the common ratio of a geometric sequence, then that would be take any given term and divide it by the term right in front of it. And that's what that formula would look like. In order to be an arithmetic or a geometric sequence, that result has to be the same no matter where you start. So for instance, if we did the geometric sequence 1, 2, 4, 8, 16, 32, notice that any term I take and divide it by the term in front of it, I'm always going to get the answer 2. So like 32 divided by 16, that's 2. And 16 divided by 8, that's 2. And 8 divided by 4, that's 2. And that's how you essentially confirm that this really is a geometric sequence, because no matter what term you start at, if you divide by the term in front of it, you're always getting the same answer. So this test works for 2 reasons. 1, it confirms that it is a geometric sequence, and 2, it actually tells you what the common ratio is. All right, so we could use that to help us on the last problem, number 13. What type of sequence is number 13, and what's the value for D or R?
It's a geometric.
I'm sorry, I missed all that. Say that again.
It's a geometric sequence where D is times 10.
Yeah, let's take a look. So the pattern is 0.9, and then 9, and then 90, and then 900. So first of all, you can just eliminate arithmetic, because first you're adding about 8, and then you're adding 81, and then you're adding 810. So now you're not adding the same thing over and over again. But if you take any given term and divide it by the term in front of it, so 900 over 90, you get 10. And if you take that term and divide it by the one in front of it, 90 over 9, you get 10. If you take that term and divide it by the one in front of it, 9 over 9, you still get 10. And so the fact that in every single case, you're taking a term and dividing by the term in front of it, you get 10 every single time. It confirms that this is a geometric sequence, and it tells you the common ratio is 10. All right, so we're talking about sequences. We're really only looking at 2 types, the arithmetic type where you're adding a common difference, or a geometric type where you're multiplying a common ratio. And the next section is going to give us a way to find the nth term of any given sequence. So, like starting off here in these couple of examples, they tell you the first few terms. Well, what if someone then said, what's the 100th term in that sequence? Or what's the 2000th term in that sequence? Or what's the 1,000,000th term in that sequence? How could you quickly find that number? So let's see, the first one is arithmetic and the second 2 are geometric. Let's do the arithmetic one first. So look at number 14 and write it down, 3, 5, 7, 9. What are we adding by every time? 2. So D equals 2. And you could go ahead and continue the sequence. It'd be 11 and then 13 and then 15 and so on. But still, if you wanted the 100th term, you still wouldn't want to have to sit there and write it all down. So they say find an explicit formula. So these are your formulas. So the nth term for an arithmetic sequence is a sub n equals a sub 1 plus n minus 1. That's D. That's the formula. You need to memorize it. This is the explicit formula for the nth term. So essentially what you're going to do is substitute in the values for A1 and B. Because n represents the variable that you would substitute like a function if you want n equals the 50th term or n equals the 90th term. So we're going to leave n just where it is. But we are going to plug in what we know to be the first term and what we know to be the common difference. So we then substitute in the first term, which is 3. And then n minus 1 stays. And then the common difference is 2. And then we now have a formula 3 plus n minus 1 times 2. We can go ahead and simplify that, and you should. So you can distribute the 2. And you get 3 plus 2n minus 2. And then you can combine like terms, and you'd say the nth term is 2n plus 1. And that is the explicit formula for the original sequence. Are we right? Is that really the explicit formula? I mean, what could we do right now? We could certainly check the first couple and see if it works. So like, what's the first term? If I plug in 1, 2 times 1 plus 1, it better give me 3, and it does. If I want the second term, I can plug in 2, and it better give me 5, and it does. And if I want the fourth term, if I plug in 4, it better give me 9. So 2 times 4 plus 1 is 9. So yeah, the formula does seem to work. At the very least, it gives me back the terms I knew. And so now if I wanted to, I could calculate any term. So I could go ahead and calculate the 100th term, and that would be 2 times 100 plus 1, which is 201. So that's the power of the explicit formula for an arithmetic sequence. That now you can go ahead and know any term in the sequence by just plugging in that value for n. I'd just like you all to note that you can use this formula even if you're subtracting over and over again. So like, let's say that I started off with the formula 6, and I'm going to start counting down by 3s. So 6, 3, 0, -3, -6, -9, -12, and so on. So it is an arithmetic sequence, and what I'm doing is subtracting 3 every time. So my d would be -3, and my first term would be 6. And so I could go ahead and use my formula, a sub n equals a sub 1 plus n minus 1 times d. Although to be fair, I think I would prefer it if the d came in front of the n minus 1. Why would that be nice to have the d in front of the n minus 1? Yeah, it looks better. You're about to distribute, and plus in this case, I'm plugging in a negative number for the d, and that's kind of awkward to put times -3 at the end of a parenthesis. So I've got my formula here. My nth term would be the first term, which is 6, plus -3 times n minus 1. And then I get 6 minus 3n plus 3, which would be -3n plus 3. So there's my explicit formula for that sequence. What do you notice? If the sequence is counting down because you're subtracting versus if the sequence is counting up because you're adding. What can you tell just by looking at the explicit formula if it's counting up or counting down? Yeah, whatever the number is on the variable tells you if the sequence is counting up or counting down. Not only that, what is the number in front of the variable? It is the common difference, right? So just by looking at the explicit formula, you can immediately tell this formula is counting up and the common difference is 2, or this formula is counting down and the common difference is -3. Okay, so that's arithmetic. Let's try a geometric. So in the second one, number 15, we have 1, -1/2, 4th, -1/8. I'd say a really good idea is, before you do any work, is just to go ahead and guess what the next term is, or guess what the next couple of terms would be. What would the next term be? We're going from +1 to -1/2, to +4 to -1/8, so the next term should be positive, and what would it be exactly? And by the way, folks, you can go ahead and write that out as 1/1 instead of 1. So the next term would be 1/16. What would the next term be?
Negative.
A -1/32. So what are we multiplying by?
Negative.
Yeah, we're multiplying by -1/2. You can see that in a couple ways, which in order to multiply something over and over again, you'd have to be multiplying by a negative, because a positive times a negative is negative, and then a negative times a negative is positive, and so on. And we're not multiplying the numerator times anything other than 1, but the denominator we're multiplying by 2. So you can build your common ratio by saying, well, the numerator I'm multiplying by 1, and the denominator I'm multiplying by 2, and I must be multiplying by a negative, because the sign is changing over and over. So there's our common ratio. And the formula now, the explicit formula, which is given there, is the nth term is equal to the first term times r to the n minus 1. And that's just the formula for the explicit formula of a geometric sequence. So again, we would plug in what we know to be our first term and our common ratio. And we say the nth term is 1 times -1/2 to n minus 1. Notice that in the case of the arithmetic formula, we were able to distribute and combine like terms and simplify. Whereas in this formula, really we're not going to do any simplification at all. Because we're raising a number to the power of n minus 1, so you can't simplify that. And the number in front doesn't have an exponent on it, so you can't multiply the two bases together. So you just leave it. There's no simplification you have to do. Okay. That's it for the arithmetic explicit formula and the geometric explicit formula. Number 16 is a really good problem, but it's not geometric or arithmetic. I think they included it to make us, think kind of hard about a sequence, even though it's neither of those two. So let's look at that last one. 1, 4, 9, 16. What would be a formula to represent this pattern? And first of all, can we just predict what the next term would be? What are those numbers? I hope you all recognize them. 4, 9, 16. What would the next one be? Oh, recognize the numbers 4, 9, 16? The 25, why? Yeah, they're squares. So first of all, we write the 1 as 1/1. So the pattern continues. And that's 1 squared, 2 squared, 3 squared, 4 squared. So the next one would be 5 squared. And the next one would be 6 squared. The next one would be 7 squared. What's that?
Would it be like you're squaring the negative?
What negative?
Like, so it would be 7 -2 squared.
Where do you get the negative from?
She's asking if
Because
it's a
it's
negative.
a fraction.
Oh, could you rewrite it as a negative exponent? Sure, you could. You could rewrite each of these as 1 to the -1, and then 4 to the -1, and 9 to the -1. Is that what you're saying?
Yeah.
Yeah, you could. We don't have to. You could, and then you could rewrite each of those as that would actually be 1 to the -2, 2 to the -2, 3 to the -2, 4 to the -2, 5 to the -2, 6 to the -2. Is that what you're saying, Josh? Yes, absolutely. You could write it that way. I don't think we need to, because the negative exponents make it a little trickier on our audience and our brain. But we could now go ahead and ask the question, if this is the first term, and this is the second term, and this is the third term, this is the fourth term, and the fifth term, sixth term, seventh term, what is the nth term? And it's even more obvious if you actually rewrite 4, 9, 16. So the first term is 1 over 1 squared. The second term is 1 over 2 squared. The third term is 1 over 3 squared. And the fourth term is 1 over 4 squared. And the fifth term is 1 over 5 squared. And the sixth term is 1 over 6 squared. And the seventh term is 1 over 7 squared. So the nth term is 1 over n squared. So they said find an explicit formula. It would be a sub n equals 1 over n squared. So notice that is not an arithmetic sequence or a geometric sequence. It's not either of those. But nevertheless, we can write down an explicit formula that now if you wanted any particular term, like the 13th term, then you would know the 13th term is 1 over 13 squared, which is 1 over 169. So it is an explicit formula, even though it's not necessarily arithmetic or geometric. Because to get from one term to the next, you don't add something over and over, and you don't multiply something over and over. Okay. So these are similar, right? We still want to find an explicit formula. So we have 1, 2/3, 1/3, 4/27. This is a really good problem because sequences partially are just fun little riddles, a challenge, a puzzle. How are you going from one term to the next? 1, 2/3, 1/3, 4/27. It's not at all immediately obvious what's happening here. Anyone have any guesses about what the next term would be? I appreciate your face, Victor. You're like, nope. So yeah, anybody, any guesses about what would come next? Now keep in mind, because maybe you're in a math class, we're approaching this with a certain maybe attitude or energy. Whereas if you were at a party playing like charades and someone's like, here's the next question, like you'd be all excited. You'd be like, yeah, woo, let's figure out the puzzle, let's do it. So maybe. Days ago, we talked about the power of rewriting things, just rewriting it in a different form. So I want us to just look here and see what we notice. First of all, what do you notice about the denominator so far? What kind of numbers are they made of? Threes, right? You got a 3 and another 3, then a 27, which is really 3 cubed. And then what do you notice about the numerators? Well, first of all, okay, so let's practice rewriting. The art of rewriting means just start rewriting things. So like, for instance, what should we rewrite 1 as? Well, if we make that 1 over 1, 2 over 3, 1 over 3, and then 4 over 27. Now there's a couple thoughts here. One is our denominators seem to be multiples or powers of 3. And what else do we notice about the numerators? What are the numerators almost? Just got to ignore that one. What could the numerators be doing? Well, they could be doing a variety of things. But could it be 1, 2, 3, 4? Maybe. We just want to allow for the possibility that, maybe that's what the numerator is doing, is just simply counting out 1, 2, 3, 4. It's not a 3 at the top, but could it be a 3? How would I rewrite 1/3 to be 3 over something? You just multiply top and bottom by 3, right? And so now all of a sudden I have 1 over 1, 2 over 3, 3 over 9, and 4 over 27. Now we have a really good looking pattern. And in fact, we're probably done. This is good looking enough that we can predict what comes next. So what would our next numerator be? A 5. And the next denominator? So this would be 1 times 3 is 3, times 3 is 9, times 3 is 27, times 3 is? It looks like this is our pattern. And again, it wasn't immediately obvious because they wrote the 1 as a 1 instead of a fraction, and they simplified 3/9 into 1/3. And so it obfuscated, it confused what the pattern. Okay, so we could go ahead and predict what would the next be. 1, 2, 3, 4, 5, 6. And then what's the next power of 3? 81 times 3 is, anyone can calculator? 81 times 3 is 243. Okay, so it looks like we have the sequence. But the problem wants more than just our ability to recognize the sequence. The problem wants us to write down a formula. So what would the formula be? Let's look at this together. And I'm introducing a tool to you here, a really powerful tool, is to actually write down right below it. This is the first term. This is the second term. This is the third term. And this is the fourth term. And this is the fifth term. And this is the sixth term. So what's the nth term? So if we want to rewrite the nth term in terms of the variable n, we want to use the variable n, just like in all of our previous problems, we're using the variable n to represent which term you're on. We should all be able to now write down the variable expression for the numerator. Our nth term numerator would be, since the third term is 3 and the fourth term is 4, the fifth term the numerator is 5, the sixth term the numerator is 6, the nth term the numerator is n. But now what about the denominator? Again, it's very helpful to rewrite things in terms of what they are. So I'm going to rewrite this again. This is really 1 over 3 to the 0. And this is 2 over 3 to the first. And this is 3 over 3 squared. And this is 4 over 3 cubed. And this is 5 over 3 to the fourth. And this would be 6 over 3 to the fifth. So what do you notice about the exponent value?
There's one less than 10.
Yeah, it's 1 less than the numerator, right? So how could we write the denominator now? It'd be 3 to the power of
-1.
n minus 1. And that's it. That's our explicit formula. The explicit formula for this sequence now is a sub n equals n over 3 to the n minus 1. That was not at all obvious, right? That was a tricky, challenging problem, to be sure. It required a lot of rewriting, didn't it? Where did I start? Well, shoot. We started off with just looking at the sequence and just kind of making a hunch, gosh, if only that were a 3. And then we changed it to a 3. We saw the bottom was powers of 3, the top was just the counting numbers. And then again, I think it's very helpful to actually label each term with a number. That way you can replace that number with a variable and see where that pattern takes you. So I think you'll have some more problems like that to try on your homework. So let's try that for the next one. Take a look at number 18 and see what your guess would be. Keep in mind that you don't just want to predict what the next term is. You want to also write down an explicit formula. So number 18, we have 27, 64, 125, 216. Do you recognize any of those numbers? So when we started logarithms, I gave you that packet where on the first page we did powers of. And I gave you powers of 2, 2, 4, 8, 16, 32, 64. And I gave you powers of 3, 3, 9, 27, 81, 243. And I gave you powers of 5, 5, 25, 125, 625. So, and I encourage you to become generally familiar with the numbers, just so that you can at least recognize them. So let's look at these numbers. Like on the one hand, I could say 27 is really 3 cubed. 64, I could say, is 2 to the power of 2, 3, 4, 5, 6, 2 to the power of 6. But if I had thought to do it, I could also write out powers of 4, and then 4 times 4 is 16 times 4 is 64. So I could also say that 64 is 4 cubed. And then I can look at 125 and say 125, that's 5 cubed. So what have we got so far? Well, I guess it all depends on what 216 is. What's 216? On your paper, it wasn't listed to do powers of 6, but 6 times 6 is 36, and times 6 again is 216. Now, right now, you might be thinking to yourself, Mr. G, this is absurd. Does the textbook, do math textbook authors really expect me to look at the number 216 and be like, hey, that's 6 cubed? Does that seem a little unfair?
Yeah.
Okay. Yeah, maybe it seems a little unfair, but all I can tell you is that, unfortunately, for better or worse, textbooks do expect a certain amount of number familiarity from you, where you would be at least familiar with certain powers of small numbers. Now, would they expect powers of 7? Maybe, because 7 times 7 is 49, times 7 again is 343. Do they really expect any given person to be walking down the street and see 343 and say, hey, 7 cubed? Okay, no, probably not. That's asking a lot, isn't it? That would almost seem unfair. And yet, in this particular case, they are asking you to look at 216 and say, oh, hey, that's a power of 6. So if you don't have these things memorized, at the very least, you would have to just start playing around and test a hypothesis. Like, let's say that you didn't know about the 216, but you saw, hey, this is a cubed number, and this is a cubed number, and this is a cubed number, and the pattern is 3 cubed, 4 cubed, 5 cubed, then at least then you'd have a guess that this thing maybe is 6 cubed, and you type it into your calculator, and it is, and you're like, wow. And then you're like, okay, well, my guess then is that the next one is 7 cubed, which is 343, and the next one after that is 8 cubed, which is something. So then all that said, what's our pattern? So watch again, this is our first term is 3 cubed. And our second term is 4 cubed. And our third term is 5 cubed. And our fourth term is 6 cubed. And our fifth term is 7 cubed. And theoretically our sixth term is 8 cubed. I'm going to erase that so I can put up n. So what would my nth term be? Yeah, n plus 2 cubed. Because you're saying the first term is 3 cubed, and the second term is 4 cubed, and the third term is 5. And you look at the comparison between each of those numbers, and you say, well, the first term becomes 3. The first term becomes 3, and the second term becomes 2, and the third term becomes 5, and the fourth term becomes 6, and the fifth term becomes 7. And so in each of those cases, it appears that you're just adding 2 to the term number. So if the term number is n, you're doing n plus 2 cubed. So, there's 2 ways to look at what we're talking about here. On the one hand, you could look at this and say, come on, this is crazy town. Why are they expecting me to know all these high powers of numbers? But on the other hand, you can interpret this as, oh, wow, this is quite the riddle, right? This is requiring an incredible amount of playfulness from me. Playfulness. It requires playfulness to sit there and think like, well, how could that number be written? What could that number be? So what do you think? Can I convince any of you to believe me that these problems are playful? Playful instead of very, very, challenging? It's playful a little bit. Okay, well, I think that's as far as we'll get today. So, yeah. Now, last time, folks, I feel so bad. Last time I forgot to hand out your tests. After everybody left, I was like, oh, man, here's all the tests. And I didn't get to hand it back to you. So here's your test. Let me walk around. Please take a minute or two to flip through it. Look at all the questions. Come ask me if you have any questions at all. Like, for instance, if you think I graded your test incorrectly, or if you feel like I took up a point and I shouldn't have. Where's Irvin? There you are. Josh, what? Oh, sorry, Josh. There was a lot of force there. Jackie? Jessica?